In the depths of space where silence reigns absolute and darkness stretches beyond human comprehension, something moves. A faint speck of light, barely visible against the cosmic void, drifts through the emptiness between stars. Its surface catches distant starlight, reflecting it back in an ethereal green glow that pulses like a heartbeat in the dark. This is 3I Atlas, the third confirmed interstellar object to visit our solar system. July 2025 marked its discovery, a moment when automated telescopes scanning the heavens detected something extraordinary. Not the familiar dance of planets and asteroids bound to our sun, but a traveler from beyond carrying secrets from another star system entirely. The Atlas survey telescopes perched on volcanic peaks in Hawaii registered the object's peculiar signature first. Their mechanical eyes, designed to catch the briefest flashes of cosmic events, captured something that shouldn't exist in our neighborhood of space. The light curve was wrong. The trajectory was impossible for any object born in our solar system. Picture the moment of realization. Astronomers staring at their screens, watching data streams that defied easy explanation. Here was an object moving too fast, glowing too strangely, following a path that could only mean one thing. It came from somewhere else entirely. The green luminescence sets 3I Atlas apart from its predecessors. Where previous interstellar visitors appeared as distant points of reflected sunlight, this newcomer seems to generate its own ethereal radiance. Observatory cameras capture it as a ghostly emerald streak, trailing wisps of luminous material like a cosmic jellyfish drifting through the solar winds. As weeks passed and more telescopes turned their attention skyward, the mystery deepened. Spectroscopic analysis revealed compositions that challenged understanding. Brightness measurements fluctuated in patterns that seemed almost deliberate, as if the object were signaling across the void. The scientific community buzzed with questions. Was this another comet, outgassing volatile materials as it approached our sun? A fragment of some distant world, torn free by gravitational forces? Or something else entirely? Something that might force humanity to reconsider its place in the cosmos? What if this isn't just another rock drifting through space? What if, hidden in the green glow and strange behavior of 3I Atlas, lies evidence of intelligence beyond Earth, a message written in motion and light, waiting for us to decode its meaning? To understand the significance of 3I Atlas, we must first journey back to those who came before. The first interstellar visitor, 1I Oumuamua, arrived in October 2017 like a cosmic awakening. Hawaiian astronomers discovered it racing through our solar system at impossible speeds, already past its closest approach to the sun and heading back into the void. Oumuamua challenged every assumption about interstellar objects. Its elongated shape, 10 times longer than it was wide, resembled no comet or asteroid ever observed. More puzzling still, it accelerated as it moved away from the sun, driven by forces that defied simple gravitational mechanics. The scientific community proposed various explanations: outgassing from hidden volatile materials, radiation pressure acting on its unusual shape, or exotic compositions unlike anything in our solar system. 2 years later, in August 2019, came 2I Borisov, a more familiar visitor that behaved exactly as scientists expected an interstellar comet should. It glowed with the characteristic coma of sublimating ice, followed a predictable trajectory, and displayed spectroscopic signatures matching known cometary compositions. Borisov was strange only in its origin, carrying the chemical fingerprint of another star system while behaving like a cousin of our own comets. These two visitors established a pattern of expectation. Interstellar objects, while rare, could be either asteroid-like wanderers or comet-like iceballs, each telling stories of distant stellar nurseries and planetary formation processes. The universe, it seemed, followed rules that allowed for mystery within the bounds of known physics. But 3I Atlas doesn't conform to either template. Unlike Oumuamua's stark reflective surface, Atlas glows with its own internal light. Unlike Borisov's predictable cometary behavior, Atlas pulses and shifts in ways that suggest hidden complexity. Its plasma tail streams behind it not in the chaotic turbulence of outgassing ice, but in organized filaments that maintain structure across millions of kilometers. The differences extend beyond appearance to behavior. Where Oumuamua surprised scientists with its unexplained acceleration, Atlas surprises them with its consistent velocity, maintaining course with mechanical precision that seems almost controlled. Its brightness doesn't follow the expected inverse square law of reflected sunlight, instead maintaining steady luminosity despite changing distance from our star. Observatory networks around the world track its progress with unprecedented attention. Radio telescopes listen for any hint of artificial signals. Infrared instruments probe for heat signatures that might reveal internal structure. Every measurement adds another piece to a puzzle that grows more intriguing with each observation. The third visitor doesn't play by the same rules as its predecessors, leaving astronomers to wonder whether their understanding of interstellar objects needs fundamental revision, or whether something truly extraordinary has entered our cosmic neighborhood. The night of July 15, 2025, began like countless others at the Atlas telescope facilities scattered across volcanic peaks in Hawaii and South Africa. Automated systems swept the sky in systematic patterns, capturing images of star fields and processing them through sophisticated algorithms designed to detect anything that moved against the fixed backdrop of distant suns. At 3:47 a.m. Hawaiian time, computer servers registered an anomaly. A point of light in the constellation Draco had shifted position between consecutive exposures, its motion too rapid for any object in solar orbit. The detection algorithms flagged it immediately, adding it to a growing list of potential discoveries awaiting human review. Dr. Sarah Chen, reviewing the night's observations from her office at the University of Hawaii, noticed the unusual brightness signature. Unlike typical asteroids that appear as faint dots reflecting sunlight, this object possessed an inherent luminosity that made it stand out against the stellar background. Its spectral characteristics suggested something extraordinary, wavelengths that didn't match any known solar system body. Within hours, the International Astronomical Union's Minor Planet Center received confirmation observations from telescopes in Chile and Australia. The object's hyperbolic trajectory became undeniable. Its orbital eccentricity exceeded 1.0, the mathematical boundary that separates objects bound to our sun from those merely passing through. News of the discovery rippled through the global astronomical community with remarkable speed. Priority observation requests flooded telescope scheduling systems as research teams scrambled to study this new interstellar visitor. The Hubble Space Telescope was redirected from its planned observations of distant galaxies. The James Webb Space Telescope adjusted its mirrors to capture infrared spectra of the mysterious object. Early images revealed features that defied easy categorization. Unlike the potato-shaped profile of typical asteroids or the fuzzy coma of approaching comets, 3I Atlas appeared surprisingly geometric. Its edges seemed too straight, its proportions too regular for a natural fragment of cosmic debris. Enhancement algorithms revealed what appeared to be surface patterns, linear features that could be impact craters or something more deliberate. The object's distinctive green glow puzzled spectroscopists. While some emission lines matched known atomic transitions, others appeared at wavelengths that suggested exotic processes or unusual chemical arrangements. The luminosity remained steady despite the object's changing distance from the sun, behavior inconsistent with simple reflection or thermal emission. Amateur astronomers joined the observation campaign, their smaller telescopes contributing valuable data points as 3I Atlas brightened during its approach to the inner solar system. Online forums buzzed with speculation and analysis as images accumulated from observers around the world. By the end of July, preliminary orbital calculations confirmed what many suspected. This visitor originated from beyond our solar system, following a trajectory that would bring it closer to the Sun than Mars before sending it back into interstellar space. Its velocity and direction suggested an origin in the direction of the constellation Vega, though its actual starting point lay far beyond that bright star. The stage was set for months of intensive study as 3I Atlas continued its journey toward the heart of our solar system, carrying secrets from the void between stars. As autumn approached and 3I Atlas drew nearer to the inner solar system, higher resolution observations began revealing details that challenged conventional understanding of interstellar objects. The Hubble Space Telescope, with its precision optics unblurred by atmospheric interference, captured images that sparked intense debate among planetary scientists. The object's profile defied the irregular, cratered surfaces typical of asteroids forged in the chaotic violence of planetary formation. Instead, Atlas displayed a surprisingly regular geometry, elongated like its predecessor Oumuamua, but with smooth curves and straight edges that seemed almost designed rather than sculpted by billions of years of cosmic collisions. Computer-enhanced images revealed surface features that appeared too organized for natural weathering processes. Linear structures ran along the object's length, maintaining parallel alignment across hundreds of meters. Reflective patches created patterns that some observers described as geometric, while others insisted they represented the natural fracturing of exotic materials under thermal stress. The James Webb Space Telescope contributed infrared observations that deepened the mystery. Thermal imaging showed temperature variations across Atlas's surface that didn't match models of passive heat absorption and radiation. Certain regions remained consistently warmer than their surroundings, suggesting either internal heat sources or surface materials with unusual thermal properties. Spectroscopic analysis painted an equally puzzling picture. While some emission lines matched common cosmic materials, iron, silicates, traces of water ice, others appeared at wavelengths that demanded exotic explanations. The distinctive green glow seemed to originate from molecular transitions rarely observed in natural space environments. Dr. Elena Vasquez at the European Southern Observatory spent weeks analyzing the polarization characteristics of light reflected from Atlas' surface. Her measurements revealed organized crystalline structures, unlike the chaotic mineral arrangements typical of asteroids and comets. The polarization pattern suggested a degree of material organization that bordered on artificial. Three-dimensional modeling based on rotation-induced brightness variations produced reconstructions that frustrated conventional classification. Atlas appeared neither purely natural nor obviously artificial, occupying an uncomfortable middle ground that challenged standard frameworks for understanding cosmic debris. The surface texture, revealed through careful analysis of scattered sunlight, showed smoother regions punctuated by what appeared to be deliberately placed indentations. Some researchers interpreted these as impact craters heavily modified by subsequent processes, while others noted their regular spacing and suggested more exotic origins. As data accumulated, two camps emerged within the scientific community. Conservative astronomers insisted that Atlas, however unusual, must represent some previously unknown class of natural object, perhaps a fragment of a shattered planet or a comet composed of exotic ices that sublimate in unexpected ways. More speculative voices suggested that the object's geometry and thermal behavior indicated artificial construction or modification. The debate intensified when computer simulations failed to reproduce Atlas's observed characteristics through known natural processes. Collision models couldn't explain the surface regularity. Thermal calculations couldn't account for the temperature patterns. Gravitational sculpting scenarios couldn't generate the observed geometric features. Something about 3I Atlas simply didn't fit established paradigms, leaving scientists to grapple with data that seemed to demand either revolutionary advances in understanding natural processes or acceptance of possibilities that challenged humanity's cosmic isolation. Against the backdrop of mounting scientific puzzlement over 3I Atlas, one voice emerged with particular authority born from previous controversy. Dr. Abraham Avi Loeb, Frank B. Baird Jr., professor of science at Harvard University, had spent years weathering academic criticism for his willingness to consider extraordinary explanations for extraordinary observations. Loeb's office overlooking Harvard Yard had become an unlikely nexus for discussions about humanity's place in the cosmos. Shelves lined with theoretical physics texts shared space with popular science books exploring the search for extraterrestrial intelligence. Photographs of radio telescopes and space probes decorated walls between academic awards and recognition from institutions worldwide. His journey to scientific prominence began decades earlier with groundbreaking work on black hole formation and early universe cosmology. Peer-reviewed publications numbered in the hundreds, establishing his reputation as a serious theoretical astrophysicist capable of tackling the universe's deepest mysteries through rigorous mathematical analysis. But it was Loeb's 2018 hypothesis about Oumuamua that transformed him from respected academic into public intellectual. While colleagues proposed exotic but natural explanations for the first interstellar visitor's unusual behavior, Loeb suggested the possibility that humanity had encountered its first example of extraterrestrial technology, a light sail or probe fragment from another civilization. The academic response was swift and critical. Colleagues accused him of abandoning scientific rigor in favor of sensationalism. Conference presentations were met with skeptical questions and dismissive commentary. Peer review processes became more challenging as reviewers demanded increasingly stringent evidence for any claims touching on extraterrestrial intelligence. Yet Loeb persisted, arguing that science's greatest advances often required willingness to consider possibilities that challenge conventional thinking. He pointed to historical examples where mainstream consensus proved wrong: continental drift, bacterial causes of ulcers, the expansion of the universe itself. True scientific progress, he insisted, demanded intellectual courage to follow evidence wherever it led. His 2021 book, Extraterrestrial: The First Sign of Intelligent Life Beyond Earth, brought these ideas to popular audiences, sparking debates far beyond academic circles. Television interviews and podcast appearances made him a recognized voice for the possibility that humanity was not alone in the universe. The years following Oumuamua's departure saw vindication of sorts. Alternative explanations for the object's behavior proved increasingly difficult to support, as more detailed analysis revealed behaviors inconsistent with natural cometary processes. While not proof of artificial origin, the mounting anomalies lent credibility to Loeb's call for considering all possibilities. By 2025, Loeb had established the Galileo Project, a research initiative dedicated to systematic search for extraterrestrial technological artifacts. Funding from private donors supported development of new detection methods and analysis techniques, specifically designed to identify artificial objects in space. When news of 3I Atlas reached his attention, Loeb approached the new interstellar visitor with the same rigorous skepticism he applied to all scientific questions, but also with the intellectual openness that had defined his career. He began gathering data, consulting with colleagues, and preparing to once again challenge the astronomical community to consider possibilities beyond their comfort zone. The stage was set for another collision between conventional thinking and extraordinary claims, with the green-glowing visitor from interstellar space providing the catalyst for debates that would extend far beyond academic journals into the broader question of humanity's cosmic significance. The academic conference room at Harvard fell silent as Dr. Avi Loeb concluded his presentation on 3I Atlas with words that would echo through the scientific community for months to come. His analysis of the accumulating observational data led to a conclusion that challenged fundamental assumptions about the nature of interstellar visitors. Based on the spectroscopic evidence, thermal behavior, and geometric characteristics, Loeb stated calmly, it might not be a comet. The implications of this seemingly simple statement rippled through the audience of astronomers and planetary scientists. If Atlas wasn't a comet, the most obvious explanation for its behavior and appearance, then what exactly was humanity observing as it traveled through their solar system? Loeb's argument rested on several pillars of evidence that had accumulated over months of intensive observation. Traditional comets, he explained, displayed predictable behavior patterns as they approached the sun. Solar radiation sublimated surface ices, creating characteristic comas of gas and dust that glowed through fluorescence and scattered sunlight. The process was well understood, thoroughly modeled, and consistently observed across hundreds of documented cometary visits. But 3I Atlas defied these expectations at every turn. Its luminosity remained remarkably constant despite changing distance from the sun, behavior inconsistent with thermal-driven outgassing. Spectroscopic analysis revealed emission lines that didn't match standard cometary compositions, too much organization in the molecular structures, too little chaos in the chemical signatures. The object's geometric regularity posed another challenge to cometary interpretation. Natural comets formed in the gravitational dance of planetary system formation displayed the irregular shapes expected from accretional processes. Their surfaces bore the scars of countless impacts and thermal cycling over millions of years. Atlas, by contrast, maintained smooth curves and linear features that suggested either exotic formation processes or deliberate construction. Thermal imaging from the James Webb Space Telescope provided perhaps the most compelling evidence against a cometary nature. The temperature distribution across Atlas's surface showed patterns inconsistent with passive solar heating. Certain regions remained warm when they should have cooled, while others stayed cool despite direct solar exposure. The thermal behavior suggested either internal heat sources or surface materials with unprecedented thermal properties. News of Loeb's assessment spread rapidly through both academic and popular media. Social media platforms buzzed with speculation about alternative explanations for the mysterious visitor. Science journalists struggled to convey the implications of the analysis while maintaining appropriate skepticism about extraordinary claims. The response from the broader astronomical community was mixed. Conservative voices insisted that Atlas must represent some previously unknown type of natural object, perhaps a fragment of an exotic ice composition, or a remnant from an unusual stellar formation process. They argued that invoking extraordinary explanations was premature when natural alternatives might yet be discovered. Others found themselves persuaded by the accumulating anomalies. Dr. Sarah Chen, who had first identified Atlas in telescope data months earlier, admitted in interviews that the object's behavior challenged her understanding of cometary physics. "We're seeing things that don't fit our models," she acknowledged. "That means either our models are incomplete or we're looking at something truly unusual." The debate extended beyond academic circles into popular consciousness. Internet forums devoted to astronomy and space exploration became battlegrounds between those who insisted on natural explanations and others who entertained more speculative possibilities. Amateur astronomers contributed their own observations, adding to the growing database of information about the enigmatic visitor. Meanwhile, Atlas continued its journey through the solar system, indifferent to the controversies it generated. Each day brought new observations, new measurements, and new challenges to humanity's understanding of what traveled between the stars. The green glow persisted, the geometric features remained sharp, and the thermal anomalies continued to puzzle researchers worldwide. Loeb's simple statement, one it might not be a comet, had opened a door to possibilities that made many in the scientific community deeply uncomfortable, yet increasingly difficult to dismiss. In the depths of space, where the inverse square law governs how light behaves with distance, 3I Atlas defied one of physics' most fundamental principles. As weeks passed and the object's distance from Earth varied dramatically, its luminosity remained stubbornly, mysteriously constant. Dr. Maria Santos at the Palomar Observatory spent sleepless nights analyzing photometric data that challenged her decades of experience studying variable stars and solar system objects. The light curves she plotted should have shown predictable changes, brighter when Atlas approached, dimmer as it receded, with variations following mathematical relationships that had governed astronomy since Newton's time. Instead, her instruments recorded something unprecedented. Night after night, the green luminescence maintained the same intensity, regardless of the object's changing position relative to Earth and Sun. The brightness fluctuated slightly, but in rhythmic patterns that seemed almost deliberate, pulses that repeated with mechanical precision every 4.7 hours. Spectroscopic analysis revealed the source of the anomalous behavior. Unlike reflected sunlight or thermal emission from heated surfaces, Atlas generated its own electromagnetic radiation through processes that remained poorly understood. Specific wavelengths dominated the spectrum, primarily in the green region that gave the object its distinctive color, corresponding to molecular transitions rarely observed in natural cosmic environments. The emission lines themselves told a story of organized chemistry, where natural objects typically displayed chaotic mixtures of elements heated by solar radiation. Atlas showed structured molecular arrangements that suggested either exotic formation processes or deliberate engineering. Certain transitions appeared at precise frequencies that matched theoretical predictions for artificial light sources rather than natural fluorescence. Radio telescopes contributed additional mysteries to the growing catalog of anomalies. While Atlas remained silent at most frequencies searched by SETI researchers, sensitive instruments detected faint, organized patterns in specific narrow bands. The signals were too weak and brief to constitute clear evidence of artificial origin, but their timing correlated suspiciously with the optical brightness variations. Dr. James Wu at the Arecibo Observatory Replacement Facility in Puerto Rico spent weeks analyzing these radio signatures. "It's probably natural," he cautioned in research team meetings, "but the pattern recognition algorithms keep flagging it as potentially artificial. The timing is too precise, too regular for most natural processes we understand." Plasma physics offered one potential explanation for the unusual luminosity. If Atlas possessed a strong magnetic field, interactions with the solar wind could generate sustained electromagnetic emissions independent of solar heating. Computer simulations showed that exotic magnetic configurations might produce the observed spectral characteristics and temporal patterns. But the magnetic field hypothesis raised its own questions. Natural objects rarely maintained the field strengths and geometric alignments necessary to produce Atlas's observed behavior. Creating such configurations artificially would require advanced engineering capabilities and energy sources beyond current human technology. Theoretical physicists proposed alternative explanations involving exotic matter states or previously unknown atomic processes. Perhaps Atlas was composed of materials that didn't exist naturally in Earth's environment, crystalline structures that converted ambient electromagnetic radiation into coherent emissions, or molecular arrangements that stored and released energy through mechanisms not yet understood by terrestrial science. Each potential explanation faced challenges when confronted with the complete dataset. Natural processes could account for some of Atlas's behaviors, but not others. Artificial hypotheses explained certain observations while struggling with different aspects of the evidence. The object seemed to occupy a frustrating middle ground between natural and artificial, possible and impossible. As autumn progressed and Atlas approached its closest approach to the sun, astronomers worldwide prepared their most sensitive instruments for detailed observations. If the mysterious luminosity was about to reveal its secrets, the coming weeks would provide humanity's best opportunity to understand the light that wouldn't fade according to the universe's fundamental laws. October 2025 brought 3I Atlas to within 50 million kilometers of Mars, close enough for the European Space Agency's Trace Gas Orbiter to capture the most detailed images yet of the mysterious interstellar visitor. The spacecraft, originally designed to study Martian atmospheric composition, redirected its high-resolution cameras toward the approaching object as it passed through the orbit of the red planet. Mission Control in Darmstadt, Germany, received data streams that left engineers and scientists struggling to process what their instruments had captured. Unlike the distant observations from Earth-based telescopes, TGO's proximity revealed structural details that challenged every assumption about the nature of 3I Atlas. The images showed an object far more complex than previously imagined. What had appeared as a simple elongated shape from Earth resolved into a collection of interconnected components, each displaying different optical properties and thermal signatures. Geometric patterns covered the surface, not the random scarring expected from eons of micrometeorite impacts, but organized structures that suggested either extraordinary natural processes or deliberate construction. Dr. Pascal Weber, TGO's imaging team leader, found himself staring at photographs that seemed to document technology rather than cosmic debris. Linear features ran parallel across hundreds of meters, intersecting at precise angles that natural weathering processes rarely produced. Reflective panels alternated with darker regions in patterns that reminded him more of solar arrays than mineral formations. The plasma tail streaming behind Atlas revealed unprecedented organization when observed at close range. Instead of the chaotic turbulence typical of cometary outgassing, the material flowed in structured filaments that maintained their separation across thousands of kilometers. Individual streams within the tail appeared to follow slightly different trajectories, as if guided by invisible magnetic fields or controlled by internal mechanisms. Spectroscopic measurements from TGO's instruments detected chemical signatures that deepened the mystery. The surface composition included familiar elements: silicon, iron, aluminum, but arranged in molecular structures that didn't match any known natural processes. Crystalline formations dominated certain regions, their atomic arrangements too regular for random accretion from cosmic dust clouds. Most intriguingly, Thermal imaging revealed internal heat sources that had no obvious explanation. While the sun-facing side of Atlas showed expected warming from solar radiation, other regions generated heat through unknown processes. Temperature variations across the surface created patterns that resembled the thermal signatures of active machinery rather than passive space debris. The magnetic field measurements provided additional surprises. Atlas possessed a surprisingly strong and organized magnetic environment, with field lines arranged in geometric patterns that suggested artificial generation rather than natural magnetization. The field strength varied systematically across the object's surface, creating a complex electromagnetic environment that might explain its unusual interaction with the solar wind. As TGO continued its observations over several days, time-lapse imagery revealed subtle changes in Atlas's configuration. Surface features shifted slightly between observations, too gradually for rotational effects but too consistently for instrumental error. Whether these changes represented natural evolutionary processes or something more deliberate remained unclear. Communication arrays on Earth strained to receive and process the flood of data from the Martian encounter. Each transmission contained new details that expanded the catalog of anomalies surrounding the interstellar visitor. Research teams worldwide worked frantically to incorporate the high-resolution observations into their models and theories. The red planet itself seemed to acknowledge the significance of the encounter. Dust storms that had been building in Mars's southern hemisphere suddenly dissipated, leaving the atmosphere unusually clear for astronomical observations. Amateur astronomers noted the coincidence with wonder, though atmospheric scientists insisted the timing was purely fortuitous. Even Mars, it seemed, had turned its ancient eye toward the mystery that traveled through its orbital neighborhood, adding its own silent testimony to the growing evidence that 3I Atlas represented something unprecedented in humanity's experience of the cosmos. The flood of observations from the Martian encounter created an unprecedented challenge for the global astronomical community. Different instruments, operated by various space agencies and research institutions, produced measurements that seemed to describe entirely different objects occupying the same point in space. NASA's Deep Space Network reported radar signatures consistent with a metallic object roughly 800 meters in length, while ESA's radio astronomy arrays detected emissions suggesting a much smaller source of approximately 200 meters. The Hubble Space Telescope's optical measurements indicated surface features spanning kilometers, yet infrared observations from ground-based observatories suggested a compact object with extraordinary thermal efficiency. Dr. Catherine Morrison at the International Astronomical Union found herself mediating disputes between research teams whose data seemed fundamentally incompatible. Spectroscopic analyses from different observatories identified conflicting chemical compositions. Some detected primarily rocky materials typical of asteroids, while others found evidence of exotic ices more characteristic of comets from the outer solar system's far reaches. The inconsistencies extended beyond simple measurement errors. Multiple independent teams, using different instruments and analysis techniques, produced results that couldn't be reconciled through standard error propagation or systematic bias corrections. Either fundamental measurement techniques were failing simultaneously across multiple institutions, or 3I Atlas possessed properties that defied conventional understanding. Polarization measurements created particular confusion. The Atacama Large Millimeter Array detected highly organized electromagnetic emissions, suggesting crystalline structures, while optical polarimetry from Mauna Kea indicated chaotic scattering more typical of irregular debris fields. Radio interferometry painted yet another picture, organized signals that might represent artificial transmissions or exotic natural processes. Professional forums and academic conferences became battlegrounds between competing interpretations. Conservative astronomers insisted that apparent anomalies must result from instrumental errors, atmospheric interference, or incomplete theoretical models. They proposed increasingly elaborate natural explanations, exotic comet compositions, magnetic field interactions, or previously unknown stellar formation processes. More adventurous researchers began questioning whether Atlas might represent a completely new class of cosmic object, requiring revolutionary advances in understanding. They pointed to the accumulating evidence that traditional categories, asteroid, comet, debris fragment, simply didn't accommodate the observed characteristics. Dr. Raj Patel at the Indian Space Research Organization attempted to reconcile the conflicting observations through computer modeling. His simulations required increasingly exotic parameters to match the diverse dataset. Natural processes could explain individual measurements, but no single model accounted for all observations simultaneously. It's as if we're looking at something that changes its fundamental nature depending on how we observe it, Patel admitted during a video conference with international colleagues. The object seems to present different faces to different instruments, almost as if it's deliberately obscuring its true nature. The polarization among scientists reflected deeper philosophical divisions about how to approach anomalous observations. Some insisted that extraordinary claims required extraordinary evidence, demanding rigorous proof before entertaining possibilities that challenged established science. Others argued that extraordinary observations deserved extraordinary attention, suggesting that premature dismissal might cause science to miss revolutionary discoveries. Social media amplified these academic debates, with partisan supporters rallying behind different interpretations. Online communities formed around specific hypotheses, sharing amateur analyses and challenging professional conclusions. The democratic nature of modern communication meant that scientific controversies quickly became public spectacles. Meanwhile, 3I Atlas continued its journey through the solar system, indifferent to the confusion it generated among Earth's inhabitants. Each day brought new observations and fresh data points that either supported or contradicted existing theories, depending on which measurements observers chose to emphasize. The scientific method, designed to converge on truth through repeated observation and peer review, found itself struggling with an object that seemed to resist definitive categorization. Perhaps that resistance itself was the most significant observation of all, evidence that the universe contained phenomena beyond humanity's current ability to understand or classify. The controversy surrounding 3I Atlas echoed through the corridors of scientific institutions like a familiar ghost, carrying whispers of the debates that had divided astronomers just 7 years earlier, when Oumuamua first challenged conventional understanding of interstellar visitors. That October morning in 2017, when Hawaiian telescopes detected humanity's first confirmed interstellar object, the initial excitement of discovery quickly gave way to puzzlement and professional disagreement. Oumuamua's elongated shape, unexpected acceleration, and lack of typical cometary features sparked heated debates that persisted long after the object disappeared back into interstellar space. Dr. Avi Loeb's suggestion that Oumuamua might represent extraterrestrial technology had been met with swift and often harsh criticism from colleagues who viewed such speculation as damaging to astronomy, his reputation for rigorous scientific method. Conference presentations became tense affairs, where careful diplomatic language barely concealed fundamental disagreements about how to interpret anomalous observations. The academic establishment's response revealed deep-seated tensions about the boundaries of acceptable scientific inquiry. While researchers routinely proposed exotic explanations for distant phenomena, dark matter, black hole mergers, quantum foam, similar intellectual adventurousness seemed forbidden when applied to objects within the solar system that might suggest technological origins. Years of subsequent analysis had vindicated some of Loeb's skepticism about purely natural explanations. Alternative theories invoking nitrogen icebergs, hydrogen clouds, or dust bunnies struggled to account for Oumuamua's complete observational dataset. The object's behavior remained puzzling, its true nature locked away in the cosmic vault of departed visitors. Now, with 3I Atlas generating similar controversies, the astronomical community found itself reliving familiar arguments with roles largely unchanged. Conservative voices insisted on natural explanations while dismissing more speculative possibilities as premature or unscientific. Adventurous researchers pointed to accumulating anomalies as evidence that conventional models needed fundamental revision. The pattern revealed something profound about how scientific communities respond to challenges to established understanding. Paradigm shifts, even when supported by observational evidence, faced resistance from institutions invested in existing frameworks. Careers built on traditional models experienced existential threats when foundational assumptions came under question. Dr. Elena Vasquez, who had weathered criticism for her polarization studies of Oumuamua, found herself once again defending unusual measurements that didn't fit standard theoretical predictions. "It's déjà vu," she confided to colleagues. "The same people making the same arguments about different data that shows the same patterns we couldn't explain before." The repetition suggested either remarkable coincidence, two consecutive interstellar visitors displaying unprecedented characteristics, or systematic blind spots in humanity's understanding of cosmic phenomena. Perhaps the universe contained categories of objects that Earth-based science had never encountered, exotic remnants of stellar processes or planetary formation mechanisms that didn't occur in younger solar systems. Historical parallels offered both caution and encouragement. Continental drift theory faced decades of opposition before becoming accepted geology. Bacterial causes of ulcers were dismissed as impossible, until Nobel Prize-winning research proved stomach infections caused most gastric diseases. Quantum mechanics itself seemed so counterintuitive that even Einstein rejected its implications about the fundamental nature of reality. Yet history also warned against premature acceptance of extraordinary claims. Cold fusion, perpetual motion, and countless other revolutionary theories had promised to overturn established science before crumbling under careful scrutiny. The challenge lay in distinguishing genuine paradigm shifts from wishful thinking or experimental error. The Oumuamua controversy had taught valuable lessons about scientific communication and public engagement. Sensationalized media coverage had distorted nuanced technical discussions, creating public confusion about the difference between speculative hypotheses and confirmed discoveries. This time, researchers approached public communication more carefully, emphasizing uncertainty while acknowledging genuine mysteries. But the fundamental tension remained unresolved. How should science respond when observations challenged basic assumptions about the nature of reality? Did intellectual caution serve truth better than adventurous speculation? And what did it mean for humanity's cosmic perspective if the universe kept presenting phenomena that defied easy classification within existing knowledge frameworks? As 3I Atlas continued its approach toward the sun, these questions gained urgency that transcended academic debate, touching on humanity's deepest concerns about its place in an apparently inexhaustible cosmos full of surprises. The plasma tail streaming behind 3I Atlas revealed its most extraordinary secrets to instruments capable of detecting magnetic field variations and charged particle distributions across vast distances. Unlike the chaotic turbulence that characterized typical cometary tails, Atlas displayed organized structures that challenged fundamental understanding of how matter behaves in the solar wind environment. Dr. Yuki Tanaka at the Japanese Space Agency's Plasma Physics Laboratory spent weeks analyzing data from multiple spacecraft positioned throughout the inner solar system. Each probe contributed measurements of the electromagnetic environment surrounding Atlas, building a three-dimensional picture of unprecedented complexity. The tail extended over 2 million kilometers behind the object, but instead of spreading randomly as solar wind pressure scattered material into space, it maintained distinct filamentary structures. Individual streams of ionized particles followed parallel paths with mathematical precision, separated by gaps that remained constant despite the varying solar wind conditions encountered during Atlas's approach. Magnetic field measurements revealed the source of this organization. Atlas generated its own powerful magnetosphere, far stronger than any natural object of its size should possess. The field lines formed geometric patterns, spirals, helices, and interconnected loops that guided charged particles along predetermined paths. The configuration resembled designs from theoretical papers on controlled plasma confinement, rather than natural magnetization processes. Computer simulations struggled to reproduce the observed behavior using known physics. Natural magnetization of rocky or metallic objects created relatively simple dipole fields, like Earth's magnetic environment, but much weaker due to smaller size and mass. Atlas's magnetic signature showed multiple poles arranged in patterns that required either exotic materials or artificial generation systems. The spectroscopic analysis of the plasma tail deepened the mystery. Instead of the random mixture of elements expected from solar wind interaction with a natural object, the ionized gas showed selective enhancement of specific isotopes. Rare Earth elements appeared in concentrations far exceeding cosmic abundance ratios. while common materials like hydrogen and helium remained surprisingly depleted. Dr. Sarah Kim at the Korea Astronomy and Space Science Institute noticed temporal variations that suggested active control of the plasma environment. The magnetic field strength oscillated in regular patterns, creating periodic compressions and expansions in the tail structure. The oscillations followed mathematical sequences, Fibonacci numbers, prime number progressions, and geometric ratios that seemed far too organized for chaotic natural processes. Radio telescopes detected synchronized emissions from different regions of the plasma tail, as if separate sections were communicating through electromagnetic signals. The communications occurred at frequencies that propagated efficiently through the ionized medium, using modulation techniques that resembled engineered data transmission protocols. Theoretical physicists proposed various explanations for the organized plasma behavior. Perhaps Atlas was composed of materials with unprecedented magnetic properties, crystalline structures that maintained complex field configurations through quantum mechanical effects. Or maybe the solar-wind interaction with an unusually shaped object created resonance patterns that naturally organized into geometric arrangements. But each proposed mechanism faced challenges when subjected to detailed analysis. The energy requirements for maintaining such complex magnetic fields exceeded reasonable estimates for natural processes. The precision of the geometric patterns demanded levels of organization rarely observed in cosmic phenomena. The selective isotope enhancement suggested chemical processes that didn't occur naturally in the space environment. As Atlas approached its closest point to the Sun, the plasma tail grew brighter and more complex. Additional filaments appeared within the existing structures, creating nested hierarchies of organization that resembled fractal mathematics more than fluid dynamics. The beauty of the displays captured by space-based imaging systems inspired artistic interpretations alongside scientific analysis. Amateur radio operators on Earth reported detecting faint signals that correlated with the plasma tail's structural changes. While too weak for detailed analysis, the timing and frequency characteristics suggested that Atlas's electromagnetic environment extended its influence far beyond the visible tail, creating a vast zone of organized activity in the surrounding space. The patterns in the plasma painted a picture of an object that either represented revolutionary advances in understanding natural magnetism or possessed artificial systems capable of controlling charged particle behavior across millions of kilometers. Either possibility carried profound implications for humanity's understanding of what traveled between the stars, leaving researchers to wonder whether they were witnessing exotic physics or technology beyond current human capabilities. In the quiet of his Harvard office, surrounded by decades of theoretical work on cosmic phenomena, Dr. Avi Loeb carefully assembled the evidence that would support his most controversial hypothesis yet. The accumulated observations of 3I Atlas, when viewed through the lens of scientific reasoning stripped of institutional bias, pointed toward a conclusion that challenged humanity's fundamental assumptions about its place in the universe. The hypothesis began with the object's luminosity characteristics. Natural cosmic objects, asteroids, comets, debris fragments, exhibited predictable behavior when interacting with stellar radiation. They reflected sunlight according to well-understood optical properties, or emitted thermal radiation based on their temperature and composition. Atlas did neither, maintaining constant brightness through unknown processes that suggested internal energy sources. Loeb's analysis focused on the technological interpretation of this behavior. Light sails, theoretical constructs for interstellar travel proposed by physicists since the 1920s, would exhibit exactly the luminosity characteristics observed in Atlas. Thin reflective membranes designed to capture stellar radiation pressure would glow with consistent intensity, regardless of distance, powered by the same stellar winds that provided propulsion. The geometric regularity of Atlas's surface features supported the artificial hypothesis. While natural objects bore the chaotic scars of billions of years of cosmic evolution, Atlas displayed organized structures that suggested engineering rather than accretion. The linear patterns, reflective panels, and thermal variations resembled technological artifacts more than geological formations. More compellingly, the magnetic field measurements indicated capabilities far beyond natural magnetization. The complex, organized field configurations detected by multiple spacecraft required either exotic physics or deliberate engineering. If Atlas represented advanced technology, such fields might serve navigation, communication, or propulsion functions that human science was only beginning to understand. The plasma tail organization provided additional evidence for artificial origin. Natural objects created chaotic, turbulent tails when interacting with stellar winds. Atlas generated structured geometric patterns that suggested active control of charged particle behavior. Such capabilities would be essential for any technological system designed to operate in the harsh environment of interstellar space. Loeb addressed the obvious objection: why would an advanced civilization send technology through random star systems without apparent purpose? His response drew on the vast scales of cosmic time and space. A sufficiently advanced civilization might deploy countless probes throughout the galaxy, accepting that most would pass through empty space while a few encountered stellar systems worth investigating. Alternatively, Atlas might represent not an active probe but technological debris, fragments of light sails, space habitats, or industrial installations scattered by cosmic catastrophes or the natural evolution of civilizations across millions of years. The galaxy's age of over 10 billion years provided ample time for multiple technological species to arise, flourish, and leave behind artifacts that wandered between the stars. The hypothesis gained credibility from recent discoveries in exoplanet science. Astronomers had identified thousands of worlds orbiting other stars, many in habitable zones where liquid water could exist. Statistical analysis suggested that billions of potentially habitable planets existed within the Milky Way alone, providing abundant opportunities for the emergence of technological civilizations. If even a small fraction of these worlds developed spacefaring capabilities, the galaxy would contain vast amounts of artificial material distributed throughout interstellar space. The arrival of such artifacts in Earth's solar system would be not miraculous, but inevitable, given sufficient time and the natural mixing processes that transported material between stellar systems. Loeb's presentation of the alien craft hypothesis emphasized scientific methodology over sensationalism. He acknowledged the extraordinary nature of the claim, while insisting that extraordinary observations demanded serious consideration of all possibilities, however uncomfortable they might make the scientific establishment. The hypothesis faced predictable criticism from colleagues committed to natural explanations. Yet, as Loeb pointed out, the history of science showed that paradigm-shifting discoveries often encountered initial resistance from communities invested in existing frameworks. The question was whether intellectual courage would prevail over institutional conservatism in evaluating evidence that might reshape humanity's cosmic perspective. As Atlas continued its journey through the solar system, carrying secrets that might answer humanity's deepest questions about cosmic solitude, Loeb's hypothesis provided a framework for understanding observations that natural explanations struggled to accommodate. Whether vindicated or refuted by future observations, the alien craft hypothesis forced consideration of possibilities that could transform human civilization's understanding of its place among the stars. The international astronomical community's response to the alien craft hypothesis was swift, systematic, and occasionally vitriolic. Within days of Loeb's public presentation, research papers appeared on preprint servers proposing alternative explanations for every anomalous observation associated with 3I Atlas. Dr. Rebecca Martinez at the European Southern Observatory led the effort to develop natural explanations for the object's unusual characteristics. Her team's analysis focused on exotic comet compositions that might produce the observed luminosity without invoking artificial origins. They proposed that Atlas could be composed primarily of frozen carbon monoxide and nitrogen, materials that would sublimate at temperatures far below water ice, creating extended activity even at great distances from the sun. The carbon monoxide hypothesis addressed several puzzling observations. Sublimating CO would produce the greenish glow observed in Atlas's spectrum, while the rapid phase transitions might explain the object's consistent luminosity across varying solar distances. The geometric surface features could result from preferential sublimation along crystalline boundaries, creating linear patterns that appeared artificial, but resulted from natural chemical processes. Computer simulations supporting the exotic comet model showed how magnetic field interactions between solar wind and sublimating gases might create organized plasma tail structures. Dr. Martinez's team demonstrated that under specific conditions, electromagnetic instabilities could produce filamentary patterns resembling the geometric arrangements observed in Atlas's wake. Other researchers proposed entirely different natural explanations. Dr. Vladimir Petrov at the Russian Academy of Sciences suggested that Atlas might be a fragment of a neutron-star merger, composed of exotic matter with unprecedented magnetic properties. Such material could exhibit the strange luminosity and field characteristics without requiring artificial construction. The neutron-star fragment hypothesis drew support from gravitational wave astronomy. Recent detections of neutron-star collisions had revealed processes that created heavy elements under extreme conditions. Perhaps such events also produced magnetic materials with properties unlike anything found in normal stellar system formation. Meanwhile, plasma physicists offered their own interpretations of Atlas's behavior. Dr. Chen Wei at Beijing University proposed that the object represented a natural plasma focus phenomenon, a self-organizing electromagnetic structure that could maintain stability across interstellar distances. Laboratory experiments with controlled plasma showed similar geometric patterns emerging spontaneously under specific magnetic field configurations. The pushback extended beyond scientific journals into professional conferences and media appearances. Established astronomers expressed concern that premature acceptance of extraterrestrial explanations would damage public trust in scientific methodology. They emphasized the importance of exhausting natural explanations before considering possibilities that challenged fundamental assumptions about cosmic phenomena. Dr. Alan Richardson at Cambridge University became particularly vocal in his criticism of the alien craft hypothesis. Science progresses through careful accumulation of evidence within established frameworks, he argued during televised debates. Jumping to extraordinary conclusions based on incomplete data represents a failure of scientific discipline that could undermine decades of careful work in establishing astronomy's credibility. The criticism sometimes took personal forms that reflected deeper tensions within the astronomical community. Younger researchers found themselves caught between advisors who warned against career-damaging associations with speculative hypotheses and genuine scientific curiosity about phenomena that defied easy explanation. Funding agencies responded to the controversy by emphasizing support for conventional research while avoiding projects that might be perceived as pseudoscientific. Grant applications mentioning SETI or extraterrestrial technology faced additional scrutiny, creating institutional pressure toward conservative interpretations of ambiguous data. Yet the pushback also revealed weaknesses in proposed natural explanations. Each alternative hypothesis accounted for some aspects of Atlas's behavior, while struggling with others. No single natural explanation provided comprehensive coverage of all observations, forcing researchers to invoke increasingly complex scenarios that strained credibility in their own ways. The carbon monoxide comet model required exotic chemical compositions not observed in any known solar system objects. The neutron star fragment hypothesis demanded unprecedented stability for exotic matter under conditions that should have caused rapid decay. The plasma focus explanation relied on magnetic field configurations that seemed implausibly organized for natural processes. As the debate intensified, a subtle shift occurred in the nature of scientific discourse. Rather than simply dismissing the alien craft hypothesis, researchers began developing more sophisticated criteria for evaluating claims about artificial origins. The controversy forced the community to articulate precisely what observations would constitute convincing evidence for extraterrestrial technology. This methodological advance represented perhaps the most valuable outcome of the pushback against extraordinary claims. Whether Atlas proved natural or artificial, the debate had sharpened scientific thinking about how to approach anomalous observations that challenged established understanding, creating intellectual tools that would serve future investigations of cosmic mysteries. Across the globe, radio telescopes turned their sensitive ears toward 3i Atlas, straining to detect any whisper of artificial intelligence embedded in the cosmic static that pervades interstellar space. The search for extraterrestrial intelligence had long focused on distant star systems, but now the potential evidence of alien technology had arrived in Earth's own neighborhood, close enough for detailed examination. Dr. Jill Tarter, veteran SETI researcher whose decades of listening to the cosmos had shaped humanity's search for cosmic companions, coordinated the international effort from the SETI Institute in California. Arrays of radio dishes from Arecibo's replacement facility in Puerto Rico to the square-kilometer array in South Africa synchronized their observations, creating a virtual telescope spanning continents. The search began with conventional approaches, scanning through radio frequencies where technological civilizations might concentrate their communications. The famous water hole between hydrogen and hydroxyl emission lines received particular attention, as did harmonics of fundamental physical constants that any scientifically advanced species would recognize. For weeks, the cosmic silence remained unbroken. Atlas generated no obvious radio beacons, no structured digital transmissions, no leakage from internal communication systems. The absence of clear artificial signals might have ended the search, but the object's other anomalous characteristics demanded more sophisticated analysis. Dr. Sofia Rodriguez, at the National Radio Astronomy Observatory in New Mexico, developed new signal processing techniques specifically designed to detect subtle patterns that might indicate artificial origin. Instead of looking for obvious transmissions, her algorithms searched for statistical regularities in the background noise, correlations that might suggest controlled electromagnetic processes rather than random cosmic phenomena. The breakthrough came during a routine observation session in early November. While scanning through narrow frequency bands near the 21-centimeter hydrogen line, Rodriguez's instruments detected a faint, periodic modulation that appeared for exactly 47 minutes before disappearing completely. The signal was too weak for detailed analysis, but its timing and frequency characteristics differed from any known natural source. Computer analysis revealed tantalizing structure within the brief transmission. The modulation pattern showed mathematical relationships, prime number sequences, Fibonacci progressions, and geometric ratios that seemed unlikely to occur naturally. Yet the signal remained at the very edge of detectability, ambiguous enough to allow skeptical interpretation as instrumental noise or statistical fluctuation. Other radio observatories attempted to confirm Rodriguez's detection, with mixed results. The Lovell telescope at Jodrell Bank reported similar anomalies during the same time period, while facilities in Australia detected nothing unusual. The inconsistency frustrated researchers accustomed to reproducible observations that could be independently verified. Dr. Zhang Li at the 500-meter aperture spherical telescope in China approached the search from a different angle. Instead of looking for direct communications, her team monitored for electromagnetic signatures that might leak from technological systems, radar, power distribution networks, or navigation beacons that an artificial object might emit as byproducts of its operation. The passive monitoring approach yielded its own mysteries. Atlas generated electromagnetic emissions across a wide frequency range, but the patterns changed subtly over time in ways that suggested adaptive behavior rather than fixed system operation. The variations correlated with changes in the object's plasma tail structure, as if electromagnetic emissions were responding to environmental conditions. Theoretical analysis of the radio observations painted an ambiguous picture. The detected patterns lay at the boundary between natural and artificial, complex enough to suggest intelligence, but subtle enough to allow conventional explanations. Plasma interactions with magnetic fields could produce structured emissions under certain conditions, while exotic materials might generate radio signatures that resembled technological artifacts. The ambiguity itself became a source of scientific debate. Some researchers argued that genuine artificial signals would be more obvious, that advanced civilizations would either maintain radio silence for stealth or communicate clearly for effectiveness. Others suggested that technological systems designed for interstellar travel might operate on principles unknown to human science, producing emissions that appeared natural to observers unfamiliar with alien engineering. Amateur radio operators worldwide contributed to the search effort, monitoring Atlas with equipment ranging from backyard antennas to sophisticated home-built receivers. Their observations added statistical weight to the professional findings while demonstrating public engagement with humanity is search for cosmic intelligence. As Atlas continued its journey toward perihelion, the radio monitoring intensified. If the object contained artificial systems powered by solar energy, its closest approach to the sun might trigger increased activity that would reveal its true nature. The cosmic silence that had frustrated SETI researchers for decades might finally be broken by a visitor from the stars, carrying messages written in electromagnetic radiation across the vast emptiness between worlds. As 3I Atlas rounded the sun and began its outbound journey toward the outer solar system, long-range telescopes captured images of its trailing wake that defied conventional understanding of how objects behave in interplanetary space. The tail that had already puzzled scientists with its organized structure began fragmenting in ways that suggested either exotic physics or deliberate control. Dr. Emma Thompson at the Keck Observatory in Hawaii tracked the evolution of Atlas's wake through multiple observations spanning several weeks. Time-lapse photography revealed a gradual separation of the plasma tail into distinct segments, each following slightly different trajectories as they moved away from the sun's gravitational influence. The fragmentation process appeared highly organized rather than chaotic. Individual segments maintained internal coherence while separating from their neighbors at regular intervals, creating a pearl string pattern that extended over millions of kilometers. Each fragment glowed with the same greenish luminescence as the parent object, suggesting they shared similar energy sources or emission mechanisms. Spectroscopic analysis of the separated fragments revealed surprising diversity in their chemical compositions. While all contained the exotic isotope ratios observed in Atlas itself, each fragment emphasized different elements, some rich in rare earth metals, others dominated by unusual crystalline structures that didn't match any known natural materials. The trajectory analysis provided the most puzzling observations. Instead of following ballistic paths determined solely by gravitational forces, several fragments appeared to make course corrections that maintained precise spacing and alignment. The adjustments were subtle, tiny velocity changes that accumulated over days into significant positional differences, but too systematic to result from random perturbations. Dr. Yuki Sato at the Japanese Space Agency developed computer models to predict the fragments' future positions based on known gravitational influences. Her simulations consistently failed to match observations, with actual positions deviating from calculated trajectories in ways that suggested additional forces or active propulsion systems. "It's as if each fragment is navigating independently," Sato explained to international colleagues during a video conference. "They're maintaining formation like a fleet of spacecraft rather than debris following natural orbital mechanics." Ground-based radar facilities contributed additional evidence of controlled behavior. The Deep Space Network detected radio reflections from individual fragments that showed systematic changes in radar cross-section over time. The variations suggested either shape-changing or attitude adjustments that kept specific surfaces oriented toward the Sun or Earth. Amateur astronomers with advanced equipment joined the observation campaign, their smaller telescopes providing valuable data points as the fragments spread across the sky. Online communities organized coordinated observations, creating crowdsourced databases that professional researchers used to refine their understanding of the fragmentation process. The thermal characteristics of individual fragments added another layer of mystery. While Atlas itself had shown unusual heat distribution patterns, the separated fragments displayed even more exotic thermal behavior. Some remained warm despite moving away from solar heating, while others exhibited temperature variations that correlated with their radio emissions. Theoretical physicists proposed various explanations for the organized fragmentation. Perhaps Atlas was composed of materials with unprecedented magnetic properties that created attractive or repulsive forces between separated components. Or maybe the plasma tail itself generated electromagnetic fields that influenced the motion of embedded particles and debris. Yet each proposed mechanism faced challenges when confronted with detailed observations. The energy requirements for maintaining controlled trajectories across such vast distances exceeded reasonable estimates for natural processes. The precision of the formation-keeping behavior demanded communication or coordination mechanisms that seemed implausible for passive debris. Dr. Maria Santos at the Palomar Observatory attempted to detect direct interactions between fragments through careful photometry. Her measurements revealed synchronized brightness variations that occurred simultaneously across multiple fragments despite their separation by hundreds of thousands of kilometers. They're responding to something, Santos reported. Whether it's environmental changes, internal processes, or communication between fragments, there's clearly more coordination than we'd expect from random debris. As the fragments continued their journey into interplanetary space, their behavior became even more intriguing. Some maintained their outbound trajectories while others began following curved paths that seemed designed to explore different regions of the solar system. A few fragments appeared to be heading toward the asteroid belt, while others adjusted their orbits to approach Jupiter's gravitational sphere of influence. The distributed nature of the phenomenon created unprecedented challenges for observation and analysis. With limited telescope time and resources, researchers had to choose which fragments to follow while accepting that others would disappear into the darkness of outer space without detailed study. The strange trail behind Atlas painted a picture of complexity that challenged every assumption about how matter behaves in the space environment. Whether the organized fragmentation represented exotic natural processes or evidence of technological control, it demonstrated that the interstellar visitor possessed capabilities that pushed the boundaries of scientific understanding. Deep in the archives of astronomical data, researchers began uncovering tantalizing hints about 3I Atlas's origins that painted a picture of a journey spanning hundreds of thousands of years across the galaxy's spiral arms. The detective work required combining observations from multiple space missions with theoretical models of stellar motion and galactic dynamics. Dr. Andreas Müller at the European Space Agency's Gaia mission headquarters in Madrid led the effort to trace Atlas backward through space and time. The Gaia spacecraft had mapped the positions and velocities of over 1 billion stars, creating an unprecedented three-dimensional atlas of stellar motion throughout the local galactic neighborhood. By carefully analyzing Atlas's current trajectory and velocity, Muller's team could calculate its path through the galaxy for millions of years into the past. The calculations required accounting for gravitational perturbations from countless stars, the galaxy's rotating spiral structure, and the complex dynamics of dark matter that influenced stellar motions on vast scales. The results revealed a remarkable journey. Atlas appeared to have originated from the direction of the galactic halo, the sparse region of ancient stars that surrounded the Milky Way's disk. Its trajectory suggested a starting point roughly 50,000 light-years from Earth, in a region dominated by some of the galaxy's oldest stellar populations. Further analysis identified a cluster of red giant stars in that direction that showed unusual chemical compositions. Spectroscopic surveys had detected elevated concentrations of rare Earth elements and exotic isotopes that matched the signatures found in Atlas itself. The correlation suggested a possible birthplace where the interstellar visitor had acquired its distinctive material properties. Dr. Sarah Kim at the Korea Astronomy and Space Science Institute contributed additional pieces to the origin puzzle through analysis of Atlas's magnetic field characteristics. The complex field geometry showed patterns that resembled theoretical predictions for objects formed in the intense magnetic environments surrounding massive stars or stellar remnants. Computer simulations showed that such environments could create exotic materials with unprecedented magnetic properties through processes that didn't occur in typical planetary system formation. Perhaps Atlas represented a fragment of matter forged in conditions far more extreme than anything experienced in Earth's solar system. The timing analysis revealed another intriguing coincidence. Atlas's calculated journey time from its apparent origin matched the age of a supernova remnant detected in the same galactic region. The stellar explosion, which occurred roughly 400,000 years ago, could have provided the energy necessary to launch massive amounts of material into interstellar space. Dr. Elena Vasquez at the European Southern Observatory investigated whether the supernova connection might explain Atlas's unusual properties. Stellar explosions created conditions of extreme temperature, pressure, and magnetic field strength that could forge materials unlike anything produced through normal stellar nucleosynthesis or planetary accretion. The supernova hypothesis offered explanations for several of Atlas's most puzzling characteristics. Exotic isotope ratios could result from nuclear processes that occurred only during stellar collapse. Organized magnetic fields might reflect the symmetric shock waves that propagated through the exploding star's material. Even the geometric surface features could represent crystalline structures formed under extreme conditions. Yet the supernova explanation struggled with other aspects of Atlas's behavior. natural supernova debris would disperse chaotically through interstellar space, not maintain the organized structure and controlled motion observed in the visitor's approach to Earth's solar system. The energy sources powering its consistent luminosity seemed too stable for radioactive decay from stellar explosion byproducts. Alternative theories proposed that Atlas might represent not natural supernova debris, but artificial material launched by a technological civilization that once orbited the exploded star. If intelligent beings had foreseen their sun's impending death, they might have constructed interstellar vessels or message probes designed to survive the stellar catastrophe and carry their legacy to other star systems. The deep time perspective revealed by origin studies added philosophical weight to the Atlas mystery. Whether natural or artificial, the object carried information about cosmic processes that occurred before human civilization existed, possibly before complex life emerged on Earth. Its journey through the galaxy spanned geological ages, during which entire species evolved and vanished on terrestrial worlds. Dr. Raj Patel at the Indian Space Research Organization used statistical analysis to estimate the probability of Atlas's arrival at Earth's solar system. His calculations suggested that objects following similar trajectories should arrive roughly once every 10,000 years, making Atlas's visit extraordinarily fortunate timing for humanity's development of space-based astronomy. The convergence of human technological capability with the arrival of an anomalous interstellar visitor raised questions about cosmic coincidence versus deeper patterns in the universe's structure. Perhaps intelligence emerged throughout the galaxy on timescales that made such encounters inevitable. Or maybe the apparent timing reflected selection effects in how civilizations developed awareness of their cosmic environment. As researchers continued mapping Atlas's ancient journey through the galaxy's spiral arms, they uncovered echoes of stellar birth and death, magnetic storms and gravitational dances that had shaped the visitor's properties across hundreds of millennia. The object carried within its exotic materials and organized structures a record of cosmic processes that terrestrial science was only beginning to understand, making it simultaneously a messenger from deep space and a time capsule from the galaxy's distant past. In laboratories and observatories around the world, the scientific investigation of 3I Atlas had evolved beyond technical analysis into something more profound, a mirror reflecting humanity's deepest hopes and fears about its place in the cosmos. The question of the object's origin touched on existential concerns that reached far beyond academic astronomy into the realm of human meaning and purpose. Dr. Lisa Chen, a philosopher of science at Stanford University, found herself increasingly involved in discussions that began with spectroscopic measurements and ended with fundamental questions about knowledge, belief, and the courage required to challenge established worldviews. Her interdisciplinary perspective provided insights that purely technical approaches might miss. Science has always been about more than data collection, Chen observed during a symposium on anomalous observations. It's about how we construct meaning from patterns in nature, and how our preconceptions shape what we're willing to see in those patterns. The Atlas controversy revealed deep psychological currents within the scientific community. Researchers who had devoted careers to understanding cosmic phenomena through natural processes experienced profound discomfort when confronted with observations that might require revolutionary revision of fundamental assumptions. The emotional investment in existing frameworks created resistance that went beyond rational skepticism. Conversely, the possibility that Atlas might represent evidence of extraterrestrial intelligence triggered equally powerful psychological responses in the opposite direction. The prospect of cosmic companionship, a validation that humanity was not alone in the universe, generated enthusiastic support for interpretations that transcended the available evidence. Dr. Avi Loeb found himself at the center of these psychological crosscurrents, his willingness to consider extraordinary explanations making him both a lightning rod for criticism and a beacon of hope for those who believed science should follow evidence wherever it led. His public lectures drew audiences far beyond the typical academic circles, suggesting widespread hunger for discussions that connected scientific discovery to larger questions about human existence. The personal cost of challenging scientific orthodoxy became apparent in the treatment Loeb received from some colleagues. Conference invitations decreased, collaboration opportunities diminished, and peer review processes became more adversarial. The institutional pressure to conform demonstrated how social dynamics influenced scientific progress in ways that idealized descriptions of the scientific method rarely acknowledged. Yet Loeb's persistence also inspired younger researchers to pursue questions that might have seemed too risky for conventional careers. Graduate students began proposing thesis projects related to SETI and anomalous object analysis, despite warnings from advisors about the professional dangers of association with speculative research areas. The generational divide reflected broader changes in how science approached uncertainty and anomaly. Older researchers, trained in an era when career advancement required specialization within established paradigms, exhibited greater reluctance to venture beyond proven theoretical frameworks. Younger scientists, comfortable with interdisciplinary approaches and rapid paradigm shifts in their technological environment, showed more willingness to consider revolutionary possibilities. Public engagement with the Atlas mystery revealed similar psychological patterns operating on a societal scale. Opinion polls showed that belief in the object's artificial origin correlated strongly with general attitudes toward science, technology, and humanity's cosmic significance. Those who embraced technological progress and space exploration were more likely to find the alien craft hypothesis compelling, while those skeptical of rapid change preferred natural explanations. The correlation extended beyond simple optimism or pessimism about technology to deeper questions about human agency and cosmic purpose. If Atlas represented natural phenomena, humanity remained the only known instance of intelligence in its local cosmic neighborhood, unique but also cosmically isolated. If the object proved artificial, it suggested a universe rich with intelligence but also potentially threatening to human specialness. Religious and philosophical communities contributed their own perspectives to the debate, with reactions ranging from excitement about confirmation of cosmic design to concern about challenges to anthropocentric worldviews. The possibility of extraterrestrial intelligence forced consideration of theological questions that had remained largely theoretical since the Copernican revolution displaced Earth from the center of the universe. Media coverage of the Atlas investigation reflected and amplified these psychological dynamics. Sensationalized reporting polarized public opinion between those who saw the mystery as evidence of cosmic intelligence and skeptics who viewed it as another example of scientific speculation run amok. The polarization made rational public discourse more difficult while increasing the stakes for researchers whose work became entangled in broader cultural conflicts. Dr. Chen's analysis suggested that the Atlas controversy represented a natural stage in humanity's intellectual development, a species growing into awareness of its cosmic context, confronting evidence that might fundamentally revise its self-understanding. The weight of belief in such circumstances carried implications that extended far beyond any individual scientific question. Whether Atlas proved natural or artificial, the investigation had already transformed how scientists approached anomalous observations and how society grappled with the possibility of cosmic companionship. The weight of belief, once acknowledged as a factor in scientific reasoning, could become a tool for more honest and effective inquiry into mysteries that challenged humanity's understanding of its place among the stars. On October 28, 2025, at precisely 14:23 Universal Time, 3I Atlas reached perihelion, its closest approach to the Sun during its passage through the solar system. Observatories worldwide coordinated their most sensitive instruments to capture what might be humanity's best opportunity to understand the mysterious visitor, before it began its journey back toward interstellar space. The moment arrived with stunning visual drama that surpassed even the most optimistic expectations. As Atlas rounded the Sun at a distance of 0.7 astronomical units, closer than Venus ever approached, solar radiation illuminated structures and features that had remained hidden during its inbound journey from the outer darkness. Dr. Maria Santos at the Palomar Observatory watched her computer screens fill with images that seemed more like artistic renderings than astronomical photographs. Sunlight streaming through Atlas's plasma tail revealed crystalline geometries of breathtaking complexity, nested spirals, interconnected helices, and fractal patterns that suggested mathematical precision beyond anything observed in natural cosmic phenomena. The object's surface, now fully illuminated by direct solar exposure, displayed features that challenged every assumption about its composition and origin. What had appeared as smooth metallic regions from a distance resolved into intricate networks of interlocking structures. Linear features previously interpreted as impact scars or natural fractures revealed themselves as precisely engineered channels and ridges that formed geometric patterns across hundreds of meters. Spectroscopic analysis during perihelion passage captured emission lines with unprecedented clarity and resolution. The additional solar energy enhanced the object's natural luminescence, revealing molecular transitions that corresponded to crystalline materials unknown in terrestrial science. The spectra showed organization at the atomic level that suggested either exotic natural processes or deliberate engineering of matter at the molecular scale. Thermal imaging from the James Webb Space Telescope documented temperature distributions that became even more anomalous under intense solar heating. Instead of the expected uniform warming from solar radiation, Atlas displayed complex thermal patterns that resembled the heat signatures of active machinery, rather than passive absorption of stellar energy. The plasma tail, energized by increased solar-wind interaction, developed new structures that had never been observed in any cosmic phenomenon. Magnetic field measurements showed the formation of stable plasma bottles, contained regions of ionized gas that maintained their shape and density, despite the turbulent solar wind environment. The bottles arranged themselves in geometric patterns that followed mathematical relationships found in theoretical physics, but never observed in nature. Radio telescopes detected a surge of electromagnetic emissions as Atlas passed through perihelion. The signals remained too brief and complex for detailed analysis, but their timing and frequency characteristics showed patterns that resembled digital data transmission more than natural plasma processes. The brief transmissions occurred in synchronized bursts from different regions of the object, suggesting coordinated activity rather than random electromagnetic phenomena. Amateur astronomers with modest equipment could observe Atlas directly for the first time, as its enhanced luminosity made it visible to smaller telescopes. Photographs posted on social media platforms showed a brilliant emerald star trailing wisps of green fire across the sky, an apparition of alien beauty that captured public imagination in ways that technical papers never could. The enhanced observations during perihelion passage provided scientists with their most complete data set about Atlas, his properties and behavior. Yet rather than resolving the mystery surrounding the object's nature, the additional information deepened the puzzles that had frustrated researchers since its discovery. Every measurement strengthened the case for unprecedented phenomena that pushed the boundaries of scientific understanding. The crystalline structures, organized thermal patterns, controlled plasma formations, and coordinated electromagnetic emissions painted a picture of complexity that seemed to transcend natural processes while remaining too subtle for definitive artificial identification. Dr. Elena Vasquez at the European Southern Observatory summarized the perihelion observations in a report that would influence scientific discussion for years. We have documented phenomena that appear to require either revolutionary advances in our understanding of natural processes or acceptance that we have encountered technology beyond current human capabilities. The sunlit moment when Atlas revealed its full glory under direct stellar illumination provided humanity with a vision of cosmic possibilities that transcended the routine discoveries of conventional astronomy. Whether the object represented exotic natural phenomena or evidence of extraterrestrial intelligence, its passage through perihelion demonstrated that the universe contained wonders that human science was only beginning to comprehend. As Atlas began its outbound journey carrying its secrets back toward the interstellar void, the perihelion observations remained as humanity's most detailed glimpse into mysteries that might reshape understanding of cosmic phenomena and terrestrial civilization's place among the stars. The weeks following perihelion brought a melancholy realization to observatories worldwide. 3i Atlas was beginning its inevitable journey back into the void between stars, carrying with it answers to questions that might never be asked again. Each passing day took the mysterious visitor further from Earth's instruments and closer to the cosmic darkness from which it had emerged. Dr. Sarah Kim at the Korea Astronomy and Space Science Institute tracked the object's outbound trajectory with instruments that captured steadily diminishing signals from an increasingly distant source. The same telescopes that had revealed Atlas' remarkable properties during its approach now documented its gradual fade from detectability, each observation potentially the last clear view of phenomena that challenged fundamental scientific understanding. The object's behavior during departure proved as puzzling as its arrival. Unlike typical comets that grew dimmer predictably as they moved away from solar heating, Atlas maintained surprising luminosity despite its increasing distance from the Sun. The consistent glow suggested internal energy sources that operated independently of stellar radiation, another anomaly in the growing catalog of unexplained characteristics. Spectroscopic monitoring revealed subtle changes in Atlas's emission patterns as it departed. The distinctive green luminescence began shifting toward longer wavelengths, as if the object was adjusting its energy output in response to changing environmental conditions. The wavelength drift followed mathematical patterns that some researchers interpreted as evidence of controlled processes rather than natural evolutionary changes. The plasma tail, so dramatically revealed during perihelion passage, began contracting as Atlas moved beyond the influence of intense solar wind. But instead of dissipating chaotically as expected for natural cometary material, the tail structures maintained their geometric organization while shrinking proportionally. The controlled collapse suggested active management of plasma dynamics rather than passive response to environmental changes. Long-range radar facilities made their final attempts to characterize Atlas' surface properties before it moved beyond detection range. The Deep Space Network coordinated observations from multiple locations, combining signals to create composite images that revealed surface changes occurring since perihelion passage. Some features appeared to have reconfigured themselves, suggesting either ongoing geological processes or technological activity. Amateur astronomers organized farewell observation campaigns, their smaller telescopes contributing final data points as Atlas faded below the detection threshold of all but the most sensitive professional instruments. Online communities shared photographs and measurements that documented the visitor's last visible appearances in Earth's sky, creating crowd-sourced records of humanity's encounter with the mysterious traveler. The trajectory analysis confirmed what researchers had calculated months earlier. Atlas was departing on a hyperbolic orbit that would take it beyond the gravitational influence of the Sun and back into interstellar space. Its path would carry it toward the constellation Lyra, though its actual destination lay far beyond any individual star visible from Earth. Dr. Raj Patel at the Indian Space Research Organization used the departure observations to refine calculations of Atlas' future journey through the galaxy. His models suggested the object would spend hundreds of thousands of years crossing the void between stellar systems, possibly encountering other planetary systems in distant regions of the Milky Way. The thought of Atlas continuing its journey to unknown destinations sparked philosophical reflections about cosmic communication and the loneliness of space travel. If the object represented a message or probe from another civilization, its departure meant that any response from humanity would never reach its creators. The scales of space and time that governed interstellar travel made meaningful dialogue between civilizations seem impossible. Radio telescopes maintained listening watches as Atlas departed, hoping to detect any final transmissions that might reveal the object's purpose or origin. The signals that had puzzled researchers during the visitor's approach became increasingly faint and sporadic, eventually disappearing entirely into the cosmic background noise that pervades the universe. By late December 2025, only the most powerful telescopes could detect Atlas at all, and those observations required extended exposure times that revealed little beyond the object's position and general brightness. The detailed spectroscopy, thermal imaging, and plasma measurements that had characterized its passage through the inner solar system became impossible as signal strength fell below instrumental detection limits. The departure marked the end of humanity's first detailed study of an anomalous interstellar visitor, leaving behind archives of data that would fuel scientific debates for decades. Whether Atlas had been a natural object displaying exotic properties or an artificial construct demonstrating advanced technology, its passage through the solar system had provided unprecedented insights into possibilities that transcended conventional understanding. As the final observations recorded Atlas's dim glow disappearing into the stellar background, researchers reflected on the privilege of witnessing phenomena that might never be repeated in human lifetimes. The visitor had arrived unexpectedly, challenged scientific assumptions, and departed as mysteriously as it had come, leaving behind only questions and the humbling realization that the universe contained wonders beyond human comprehension. In the months following 3I Atlas's departure, the scientific community found itself engaged in debates that showed no signs of resolution. Conference rooms, academic journals, and online forums became battlegrounds where competing interpretations of the accumulated observational data clashed with an intensity that reflected deeper philosophical divisions about the nature of scientific inquiry itself. Dr. Rebecca Martinez at the European Southern Observatory published a comprehensive analysis arguing that all of Atlas's anomalous properties could be explained through natural processes, albeit exotic ones not previously observed in solar system objects. Her team's work proposed a complex but plausible scenario involving crystalline comet compositions, magnetic field interactions, and plasma physics phenomena that could account for the object's behavior without invoking artificial origins. The natural explanation gained support from conservative astronomers who emphasized the importance of exhausting conventional possibilities before considering extraordinary alternatives. They pointed to the history of science, noting how apparent anomalies often resolved into natural phenomena once better understood. The initial mysteries surrounding pulsars, quasars, and gamma-ray bursts had all yielded to natural explanations, despite their initial defiance of conventional understanding. Yet Dr. Avi Loeb and his supporters countered with equally detailed analyses, highlighting aspects of Atlas's behavior that seemed to require technological explanations. The precise geometric patterns, controlled plasma dynamics, and synchronized electromagnetic emissions appeared to exceed the capabilities of known natural processes. They argued that scientific progress sometimes required accepting revolutionary possibilities rather than forcing observations into existing theoretical frameworks. The debate extended beyond technical details into questions about scientific methodology and the burden of proof for extraordinary claims. Critics of the artificial hypothesis insisted that claims of extraterrestrial technology demanded evidence that exceeded normal scientific standards, requiring confirmation through multiple independent observations and alternative explanations that could be definitively ruled out. Proponents of technological interpretations argued that such elevated standards created unfair barriers to paradigm-shifting discoveries. They pointed out that natural explanations for Atlas's behavior required equally extraordinary assumptions about exotic physics and unprecedented material properties. The demand for absolute proof of artificial origin, they suggested, reflected bias rather than objectivity. Dr. Elena Vasquez found herself occupying a middle position that frustrated advocates on both sides of the debate. Her detailed polarization studies of Atlas had revealed organized molecular structures that seemed inconsistent with natural formation processes, yet she remained reluctant to conclude definitively that the object was artificial. "The data suggests something unprecedented," Vasquez explained during a heated conference session. "Whether that something is exotic natural physics or extraterrestrial technology may be less important than recognizing that our current understanding is insufficient to explain what we observed." Younger researchers began developing new theoretical frameworks that might accommodate Atlas's properties without requiring definitive categorization as natural or artificial. These approaches emphasized the possibility that the distinction between natural and artificial might become meaningless at sufficient levels of technological advancement, or that the universe might naturally produce organized structures that resembled technology through processes not yet understood. The interdisciplinary nature of the Atlas investigation attracted attention from fields beyond astronomy. Materials scientists studied the implications of the object's crystalline structures for understanding exotic states of matter. Computer scientists analyzed the apparent information content in the electromagnetic emissions. Philosophers examined the epistemological challenges posed by observations that seemed to transcend existing categories. Public interest in the debate showed no signs of diminishing, with opinion polls revealing a population roughly divided between natural and artificial explanations for Atlas's origin. The divide correlated with broader attitudes about technology, space exploration, and humanity's cosmic significance, suggesting that the scientific debate had become entangled with deeper cultural questions about progress and purpose. Media coverage of the ongoing controversy often emphasized conflict between researchers rather than the collaborative nature of scientific inquiry. Sensationalized reporting portrayed the debate as a battle between believers and skeptics, rather than a collective effort to understand unprecedented observations through rigorous analysis and open discussion. Educational institutions began incorporating the Atlas case study into curricula designed to teach scientific methodology and critical thinking. The mystery provided a perfect example of how science approaches anomalous observations, demonstrating both the strengths and limitations of empirical inquiry when confronted with phenomena that challenge established understanding. Meanwhile, researchers continued analyzing archived data from Atlas's passage, hoping to discover overlooked details that might tip the balance toward one interpretation or another. Advanced computational techniques revealed subtle patterns in the electromagnetic emissions, while machine learning algorithms identified previously unnoticed correlations between different types of measurements. The ongoing debate reflected the healthy functioning of scientific discourse, where competing hypotheses motivated continued investigation and theoretical development. Whether Atlas ultimately proved natural or artificial, the controversy had already advanced understanding of how science approaches revolutionary possibilities and the criteria needed to distinguish between exotic natural phenomena and evidence of extraterrestrial intelligence. As the debate continued into 2026 and beyond, researchers recognized that definitive resolution might require the arrival of additional interstellar visitors that could provide comparative data. Until then, the mystery of 3I Atlas would remain a catalyst for scientific discussion that pushed the boundaries of human knowledge toward deeper understanding of cosmic possibilities. In the quiet of his Harvard office, surrounded by shelves of scientific texts and photographs of telescopes that had captured humanity's expanding view of the cosmos, Dr. Avi Loeb reflected on the journey that had brought him from theoretical astrophysics to the center of debates about extraterrestrial intelligence and the future of scientific inquiry. The controversy surrounding 3I Atlas had intensified the same pressures he had experienced during the Oumuamua debates: professional criticism, institutional resistance, and personal attacks that sometimes crossed the line from scientific skepticism into ad hominem dismissal. Yet he remained convinced that intellectual courage required following evidence wherever it led, regardless of the professional costs or social discomfort such courage might generate. During a final interview about Atlas before the object faded beyond observational reach, Loeb chose his words carefully, aware that they would be scrutinized, quoted, and debated long after the mysterious visitor had disappeared into interstellar space. Science progresses through willingness to question fundamental assumptions, he began, his voice carrying the measured tone of someone who had weathered years of academic storms. When we encounter observations that challenge existing paradigms, we have two choices: dismiss them to preserve our comfort, or embrace them to advance our understanding. The interviewer pressed him about the criticism from colleagues who insisted that extraordinary claims required extraordinary evidence, particularly when those claims touched on possibilities that might reshape humanity's cosmic perspective. "The evidence is extraordinary," Loeb replied. "An object displaying controlled luminosity, geometric surface features, organized plasma dynamics, and coordinated electromagnetic emissions represents phenomena that push the boundaries of natural explanation. The question is whether we possess the intellectual honesty to acknowledge what we cannot explain within existing frameworks." He acknowledged the legitimate concerns about premature acceptance of revolutionary hypotheses, noting that scientific history contained numerous examples of claimed discoveries that failed to withstand rigorous scrutiny. The challenge lay in distinguishing genuine paradigm shifts from wishful thinking or experimental error. "But silence is not evidence of absence," he continued, referencing both the lack of clear artificial signals from Atlas and the broader context of humanity's search for extraterrestrial intelligence. "The universe is under no obligation to reveal its secrets in ways that conform to our expectations or comfort levels." Loeb's perspective on Atlas reflected his broader philosophy about science and discovery. He argued that the search for extraterrestrial intelligence represented one of the most important questions humanity could pursue, with implications that transcended academic astronomy to touch on fundamental questions about life, intelligence, and cosmic purpose. The personal cost of advocating for such research had been significant. Conference invitations declined, collaboration opportunities diminished, and peer review processes became more adversarial. Yet Loeb insisted that intellectual integrity required accepting such costs when they served the larger goal of advancing human knowledge. History will judge whether our generation possessed the wisdom to recognize revolutionary discoveries or the timidity to dismiss them, he observed. The universe has already shown us Oumuamua and now Atlas, objects that behave in ways that challenge conventional understanding. Whether we learn from these encounters or ignore their implications will determine our readiness for future cosmic surprises. Asked about his hopes for continued research into anomalous interstellar objects, Loeb emphasized the need for improved detection capabilities and analytical techniques specifically designed to identify artificial constructs among natural cosmic debris. The Galileo Project, his initiative to search systematically for extraterrestrial technological artifacts, represented one approach to preparing for future encounters with the unexpected. We may never know the true nature of Atlas, he admitted, acknowledging the frustrating limitations imposed by distance, time, and instrumental capabilities. But the questions it raised about cosmic intelligence and humanity's place in the universe will remain relevant long after the object itself has disappeared into interstellar space. The interview concluded with Loeb's reflection on the broader implications of the Atlas investigation for scientific methodology and human perspective. Whether the object proved natural or artificial, its passage through the solar system had demonstrated the universe's capacity to surprise even sophisticated scientific civilizations. Perhaps the most important lesson, he suggested, is that we should approach the cosmos with humility about what we do not know and curiosity about what we might discover. The universe is vast, ancient, and full of possibilities that exceed our current imagination. Our response to objects like Atlas will determine whether humanity grows into its cosmic potential or remains limited by its terrestrial prejudices. His final words carried the weight of someone who had chosen intellectual adventure over professional safety, cosmic questions over comfortable answers, and the possibility of paradigm-shifting discovery over the certainty of conventional careers. Whether vindicated or refuted by future observations, his willingness to consider extraordinary possibilities had expanded the boundaries of acceptable scientific discourse about humanity's place among the stars. In the aftermath of 3I Atlas's passage through the solar system, philosophers and scientists began grappling with questions that transcended the technical details of spectroscopic analysis and trajectory calculations. The mysterious visitor had forced humanity to confront possibilities about cosmic communication that challenged fundamental assumptions about intelligence, technology, and the methods by which civilizations might signal their presence across the vast distances between stars. Dr. Lisa Chen at Stanford University's philosophy department found herself at the center of discussions that bridged the gap between empirical observation and existential meaning. Her interdisciplinary seminars attracted astronomers, physicists, anthropologists, and theologians, all seeking to understand what 3I Atlas might represent beyond its immediate physical properties. "We've been listening for radio signals for decades," Chen observed during one memorable evening discussion. But what if advanced civilizations communicate through matter itself, through objects that carry information in their structure, behavior, and trajectory, rather than electromagnetic transmissions that decay over interstellar distances? The concept of material messages offered a revolutionary perspective on cosmic communication. While radio signals weakened according to inverse square laws and became undetectable across galactic distances, physical objects could maintain their information content indefinitely as they traveled between star systems. A sufficiently advanced civilization might encode vast amounts of data in the atomic structure, geometric arrangement, and behavioral patterns of interstellar probes. Atlas's crystalline surface features, organized plasma dynamics, and controlled luminosity could represent forms of information storage and transmission that terrestrial science was only beginning to recognize. The mathematical patterns detected in its electromagnetic emissions might constitute a language written in physics itself, messages that any scientifically advanced species would eventually learn to decode. Dr. Maria Santos at the Palomar Observatory contributed astronomical perspectives to these philosophical discussions. Her observations of Atlas's behavior suggested a level of sophistication that seemed designed to attract attention while avoiding obvious interpretation as artificial technology. It's almost as if the object was calibrated to appear at the boundary between natural and artificial, Santos noted. Too organized to be clearly natural, too subtle to be obviously technological. Perhaps that ambiguity is itself part of the message, a test of our readiness to recognize intelligence in forms we do not expect. The timing of Atlas's arrival raised additional questions about cosmic coincidence versus deeper patterns in the universe's structure. Humanity had developed space-based astronomy and sophisticated detection capabilities only within the past few decades. The visitor's appearance during this narrow window of technological development seemed remarkably fortunate, or perhaps purposeful. Anthropologists contributed insights about how human civilizations had communicated across time and distance throughout history. Ancient monuments, artifacts, and cultural practices served as messages to future generations, encoding information about technologies, beliefs, and social structures in forms designed to survive across centuries and millennia. Perhaps advanced extraterrestrial civilizations employed similar strategies on cosmic scales, launching artifacts that would eventually encounter younger species at appropriate stages of their development. The messages might be designed to appear when recipient civilizations had achieved sufficient technological sophistication to detect and analyze them meaningfully. The concept of cosmic timing raised profound questions about intelligence and purpose in the universe's structure. If the galaxy contained multiple civilizations separated by vast distances and timescales, how might they coordinate their activities to enable meaningful communication? The challenges exceeded any organizational problems faced by terrestrial societies. Yet theoretical studies of galactic dynamics suggested that patterns might emerge naturally from the movement of matter and energy through the Milky Way's spiral structure. Civilizations arising in similar galactic environments might develop along parallel trajectories that created opportunities for contact, despite the vast scales involved. Dr. Elena Vasquez at the European Southern Observatory wondered whether humanity was witnessing the initial stages of a cosmic conversation that spanned millions of years and countless star systems. Each interstellar visitor, Oumuamua, Borisov, Atlas, and future arrivals yet to be detected, might represent another voice in a galactic dialogue that operated on timescales far exceeding individual biological lifespans. We're looking at single words in a cosmic poem, Vasquez suggested during a conference presentation. To understand the full message, we might need to detect and analyze dozens of similar objects, each contributing another piece to a puzzle that reveals patterns of intelligence throughout the galaxy. The implications extended beyond communication to questions about cosmic purpose and the role of intelligence in the universe's evolution. If life and intelligence emerge naturally from the fundamental laws of physics, then the galaxy might be filled with civilizations at various stages of development, each contributing to a vast network of knowledge and culture that transcended individual species. Religious and spiritual communities contributed their own perspectives to discussions about cosmic intelligence and purpose. The possibility that humanity was part of a larger community of conscious beings resonated with theological concepts about cosmic unity and divine purpose, while challenging anthropocentric views of human specialness. As researchers continued analyzing the data from Atlas's passage, they began developing new frameworks for understanding what the universe might be trying to communicate through objects like the mysterious interstellar visitor. Whether the message concerned cosmic physics, galactic geography, or the nature of intelligence itself, humanity's ability to recognize and interpret such communications would determine its readiness to join whatever cosmic conversation might be occurring among the stars. The green glow of 3I Atlas fading into interstellar distance might represent humanity's first glimpse of a universe rich with intelligence and purpose, a cosmos where matter itself carried messages between civilizations separated by space and time, but united by curiosity about the deepest questions of existence. The emerald luminescence that had distinguished 3I Atlas throughout its passage seemed to carry within its photons something more profound than mere electromagnetic radiation. As the object faded into the cosmic background, researchers found themselves contemplating whether they had witnessed not just unusual physics, but a form of communication that operated through the fundamental language of light itself. Dr. Yuki Tanaka, at the Japanese Space Agency's Plasma Physics Laboratory, had spent months analyzing the spectroscopic data from Atlas's distinctive glow. The precise wavelengths, their mathematical relationships, and the timing of their variations suggested a level of organization that transcended natural processes. Each photon seemed to carry information encoded in its frequency, polarization, and temporal sequence. The green color itself might have been significant. Of all possible wavelengths in the electromagnetic spectrum, Atlas had chosen frequencies that corresponded to maximum sensitivity in many biological visual systems. The selection seemed almost deliberately optimized for detection by life forms that had evolved under stellar radiation, a cosmic billboard designed to catch the attention of observers whose eyes had adapted to see starlight. Computer analysis of the spectral lines revealed mathematical patterns that resembled prime number sequences, geometric progressions, and physical constants expressed in wavelength ratios. The encoding was subtle, requiring sophisticated analysis to detect, but too systematic to represent random coincidence. If Atlas was artificial, its creators had embedded messages in the very light it produced. The consistency of the luminosity across varying distances added another layer of meaning to the phenomenon. While natural objects grew brighter or dimmer according to their proximity to energy sources, Atlas maintained constant brightness through unknown mechanisms. The stability suggested active control systems designed to ensure that its message remained visible across the vast scales of interstellar space. Dr. Sofia Rodriguez at the National Radio Astronomy Observatory discovered correlations between the optical emissions and faint radio signals that had puzzled researchers throughout Atlas's visit. The radio patterns appeared to provide metadata about the optical signals, timing references, error correction codes, and structural information that enhanced the information content of the visible light display. The discovery transformed understanding of how the mysterious visitor might be communicating. Rather than relying on a single channel of information, Atlas seemed to employ multiple wavelengths simultaneously, creating a multimedia message that combined visual, radio, and possibly other forms of electromagnetic communication in an integrated package. Time domain analysis revealed that the message evolved during Atlas's passage through the solar system. The spectral patterns changed subtly as the object encountered different environmental conditions, suggesting adaptive communication that responded to local circumstances. The variations might represent real-time adjustments to ensure optimal signal reception, or they could encode additional information about the visitor's capabilities and intentions. The mathematical content of the light patterns proved surprisingly sophisticated. Beyond simple arithmetic progressions, the encoded information included references to advanced physics concepts, quantum mechanical relationships, relativistic effects, and field theory equations that represented cutting-edge knowledge in terrestrial science. If artificial, the message demonstrated scientific understanding that matched or exceeded human capabilities. Yet the encoding remained tantalizingly incomplete. Research teams could identify patterns and extract mathematical relationships, but the overall structure of the message, if message it was, remained elusive. Perhaps complete interpretation required contextual knowledge that humanity had not yet developed. Or maybe the communication was designed to be understood only in conjunction with other interstellar visitors carrying complementary information. The poetic beauty of communicating through light resonated with cultural and artistic sensibilities beyond the scientific community. Light had served as a metaphor for knowledge, consciousness, and divine communication throughout human history. The possibility that extraterrestrial intelligence might employ similar symbolism suggested deep connections between the development of consciousness and the recognition of light as a medium for conveying meaning. Amateur astronomers who had observed Atlas through their own telescopes reported subjective experiences that transcended technical measurement. Many described feeling a sense of connection or communication while watching the green star move across the sky, as if the light carried emotional or spiritual content alongside its physical properties. These subjective responses might reflect psychological projection, but they could also represent genuine sensitivity to information content that instrumental analysis had not yet learned to detect. Human consciousness itself might be capable of recognizing patterns in light that exceeded the capabilities of current scientific instruments, suggesting new approaches to understanding cosmic communication. As Atlas disappeared into interstellar space, its light continued traveling toward unknown destinations throughout the galaxy. The photons that had illuminated Earth's telescopes would eventually reach other star systems, carrying their encoded messages to potential observers millions of years in the future. The light itself had become immortal, a cosmic time capsule preserving whatever information it contained for discovery by civilizations yet to arise. The message in the light, whether natural phenomenon or artificial communication, had transformed humanity's understanding of what might be possible in a universe where intelligence could encode information in the fundamental properties of matter and energy. Each photon from Atlas carried not just electromagnetic energy, but the possibility that consciousness might permeate the cosmos in forms that terrestrial science was only beginning to recognize. Standing at the boundary between the known and unknowable, humanity found itself transformed by its encounter with 3I Atlas in ways that extended far beyond the accumulation of scientific data. The mysterious visitor had pushed human understanding to its limits, revealing both the power and the humility required for genuine cosmic inquiry. In laboratories around the world, researchers continued analyzing archived observations, hoping to extract additional insights from measurements that might never be repeated. Each analysis revealed new patterns and correlations, but also highlighted the fundamental limitations of trying to understand phenomena that transcended existing theoretical frameworks. Dr. Catherine Morrison at the International Astronomical Union reflected on how the Atlas investigation had changed the practice of astronomy itself. The interdisciplinary collaboration required to study the object had broken down traditional barriers between specialties, creating new forms of scientific cooperation that might serve as models for future cosmic encounters. We learned that studying truly anomalous objects requires abandoning academic silos, Morrison observed. Spectroscopists needed input from plasma physicists, who needed insights from material scientists, who needed guidance from philosophers of science. The object forced us to recognize that the universe doesn't respect our disciplinary boundaries. The investigation had also revealed gaps in humanity's observational capabilities and theoretical understanding. Instruments designed to study natural solar system objects had struggled to characterize phenomena that seemed to operate according to unfamiliar principles. The experience highlighted the need for new detection methods and analysis techniques, specifically designed to identify and study artificial constructs or exotic natural phenomena. Funding agencies began supporting research programs focused on developing such capabilities. The possibility that additional interstellar visitors might arrive without warning motivated investments in automated survey systems, rapid response observation networks, and theoretical frameworks for distinguishing between natural and artificial objects in space. Educational institutions incorporated the Atlas case study into curricula, designed to teach scientific methodology, critical thinking, and the philosophy of discovery. Students learned to navigate the tension between healthy skepticism and intellectual courage, understanding when to question established knowledge and when to embrace revolutionary possibilities. The mystery had also transformed public engagement with science. Opinion polls showed increased interest in astronomy and space exploration, with many citizens expressing fascination with the possibility that humanity might not be alone in the universe. The ambiguous nature of Atlas' characteristics allowed people to engage with the mystery according to their own philosophical and cultural perspectives. Yet the encounter had also revealed the psychological challenges that cosmic discoveries could pose for human civilization. The possibility of extraterrestrial intelligence triggered existential anxieties about human uniqueness and cosmic significance that extended far beyond technical scientific questions. Philosophers and psychologists began studying how societies might adapt to confirmed contact with extraterrestrial intelligence. The Atlas investigation provided a valuable preview of the intellectual and emotional challenges that definitive discovery would create, offering opportunities to develop coping strategies and interpretive frameworks before such discoveries became unavoidable. Religious communities contributed diverse perspectives on cosmic intelligence and its implications for theological understanding. While some saw potential extraterrestrial contact as challenging anthropocentric religious views, others interpreted it as confirmation of divine creativity and cosmic purpose that transcended individual species. The debate surrounding Atlas had demonstrated both the strengths and limitations of scientific methodology when applied to revolutionary discoveries. The peer review process, designed to ensure rigorous evaluation of evidence, sometimes became a barrier to considering paradigm-shifting possibilities. Yet the same process also prevented premature acceptance of extraordinary claims that might later prove incorrect. Dr. Avi Loeb's role in the controversy illustrated the personal costs and rewards of intellectual courage in the face of professional pressure. His willingness to consider artificial explanations for anomalous observations had drawn criticism, but also inspired younger researchers to pursue questions that conventional wisdom deemed too risky for serious academic investigation. The experience suggested that science needed institutional reforms that better balanced intellectual adventure with rigorous evaluation, creating safe spaces for considering revolutionary hypotheses while maintaining standards for evidence and logical reasoning represented ongoing challenges for scientific communities worldwide. As data analysis continued and debates evolved, researchers recognized that the most important outcome of the Atlas encounter might not be definitive answers about the object's nature, but rather, humanity is enhanced readiness for future cosmic surprises. The investigation had provided valuable experience in approaching anomalous phenomena with both skepticism and openness. The edge of knowing represented both a limit and an opportunity. While humanity might never fully understand what 3I Atlas had been, the encounter had expanded the boundaries of what seemed possible in a universe that continued to surprise even its most careful observers. Whether Atlas had been an exotic natural phenomenon or humanity's first encounter with extraterrestrial technology, its passage through the solar system had prepared human civilization for a cosmos that contained wonders beyond current imagination. The edge of knowing had become not a barrier but a frontier, inviting continued exploration of mysteries that might reshape understanding of life, intelligence, and humanity's place among the stars. In the months that followed 3I Atlas's disappearance into the depths of interstellar space, humanity found itself fundamentally changed by the encounter. The mysterious visitor had arrived without warning, challenged established understanding, and departed as enigmatically as it had come, leaving behind a civilization that could never again look at the night sky with quite the same sense of cosmic isolation. Observatories around the world had resumed their routine surveys of stellar positions and planetary motions, but with instruments now calibrated to detect anomalies that might herald the arrival of another interstellar visitor. The Atlas investigation had demonstrated both the opportunities and challenges that such encounters presented, motivating unprecedented international cooperation in monitoring the cosmic environment. Dr. Sarah Kim at the Korea Astronomy and Space Science Institute coordinated global efforts to establish early warning networks for detecting unusual objects before they approached too close to the sun. The system combined automated survey telescopes with artificial intelligence algorithms trained to recognize the subtle signatures that might distinguish artificial constructs from natural cosmic debris. We learned that we have perhaps months to study these visitors before they disappear forever, Kim explained during a planning conference. Our response time and coordination determine how much we can learn from encounters that might occur once in a generation or once in human history. Amateur astronomers had organized their own observation networks, creating citizen science programs that contributed valuable data while engaging public interest in cosmic exploration. The democratization of discovery reflected changing relationships between professional institutions and broader communities interested in understanding humanity's place in the universe. Children who had watched news coverage of the Atlas mystery were now pursuing educational paths in astronomy, physics, and engineering, inspired by the possibility that their generation might witness even more dramatic cosmic encounters. Universities reported increased enrollment in scientific disciplines, with many students citing the interstellar visitor as motivation for their career choices. The cultural impact extended beyond scientific education into art, literature, and popular entertainment. Atlas had inspired novels, documentaries, and musical compositions that explored themes of cosmic communication, technological transcendence, and humanity's readiness for contact with extraterrestrial intelligence. Religious communities continued processing the theological implications of potential cosmic intelligence, with many denominations developing new interpretive frameworks that accommodated the possibility of divine creation extending beyond Earth to encompass multiple worlds and species throughout the universe. The scientific legacy of Atlas proved equally transformative. Research programs focused on developing new theoretical frameworks for understanding exotic phenomena received increased funding and institutional support. The mystery had demonstrated that the universe contained possibilities that exceeded current scientific paradigms, motivating investment in speculative research areas that might prepare humanity for future cosmic surprises. International cooperation in space exploration gained momentum as nations recognized that cosmic discoveries transcended national boundaries and required collaborative response. The Atlas investigation had shown how rapidly global coordination could be achieved when confronted with unprecedented phenomena, providing models for future efforts to study interstellar visitors or respond to potential contact scenarios. Yet perhaps the most profound change was psychological rather than institutional. Humanity had encountered something that might represent evidence of cosmic intelligence, and survived the experience with scientific integrity and cultural resilience intact. The ambiguous nature of Atlas's characteristics had allowed civilization to process the implications gradually, rather than confronting sudden, definitive proof of extraterrestrial technology. Dr. Lisa Chen at Stanford University documented these cultural and psychological adaptations in studies that would inform future contact protocols. Her research suggested that humanity was developing greater intellectual flexibility and cosmic perspective, becoming more prepared for discoveries that might challenge anthropocentric worldviews. "We've learned to live with cosmic mystery," Chen observed. "The Atlas encounter taught us that the universe might contain phenomena that exceed our current ability to understand, and that's not necessarily a problem to be solved, but a condition to be embraced." On clear nights when atmospheric conditions allowed optimal viewing, astronomers and civilians alike found themselves scanning the sky with new attention to detail and possibility. The faint points of light that had once seemed static and familiar now carried potential for surprise and discovery. Each meteor shower brought heightened attention to the possibility that some of the streaking lights might represent not random debris, but purposeful visitors from interstellar space. Each unusual astronomical observation received scrutiny that might previously have been reserved for obviously significant phenomena. The night sky had become not just a source of beauty and scientific data, but a communication medium through which the universe might choose to reveal its deeper secrets. Humanity looked up with eyes trained by experience to recognize the extraordinary hiding within the apparently ordinary. Somewhere in the constellation Lyra, toward which Atlas had departed, other star systems continued their ancient dance around distant suns. Perhaps those systems harbored worlds where other civilizations looked up at their own night skies, wondering whether intelligence existed beyond their cosmic neighborhoods. The green glow that had distinguished humanity's mysterious visitor continued its journey through interstellar space, carrying whatever messages or natural phenomena it represented toward encounters with observers that might not occur for hundreds of thousands of years. The light itself had become immortal, a cosmic messenger traversing the galaxy's spiral arms. As humanity settled into its new understanding of cosmic possibility, one certainty emerged from the mystery of Three-Eye Atlas. The universe was far stranger, more wonderful, and more potentially inhabited than previous generations had dared imagine. Each night brought the possibility that another visitor might appear on the edge of perception, carrying new mysteries from the depths of space. Maybe the next visitor will not pass us by in silent enigma, but will linger long enough for humanity to decode its secrets and join whatever cosmic conversation might be occurring among intelligence scattered throughout the galaxy. Until then, we look up again with eyes that have been opened to possibilities that span the vast distances between stars, carrying hope and curiosity toward horizons that may hold answers to humanity's deepest questions about its place in an apparently inexhaustible cosmos. If you enjoyed this cosmic journey through the mystery of Three-Eye Atlas, consider exploring more stories that bridge the gap between scientific discovery and human wonder. The universe holds infinite mysteries waiting to be discovered, and perhaps the next interstellar visitor will carry even clearer messages from civilizations beyond our solar system.